Hello students, in this video we'll discuss continuous whole life insurance and continuous discrete insurance. So let's recall, we have the present values for discrete insurances. A double dot x is the sum, k goes from 0 to infinity, of nu to the k. I get the present value of $1 paid at time k, provided you have survived age x to time k, x plus k. And we also had the truncated version of this. We had a double dot x n, and that was the sum, k goes from 0 to n minus 1, of nu to the k, k px. We can consider continuous analogs of these, whereas with the discrete case, this first case for the whole life, your payments start at time 0 when you are at age x. So here your age is x. You get a payment of 1, and you'll get $1 every year, provided you survive. Whereas on this temporary annuity, you start at age 0 when you are age x, and you'll get $1 every year that you survive, up to year n minus 1. And then if you survive past year n minus 1 to year n, nothing happens. The annuity will stop at that point. So that's a temporary annuity. Now what we can do is we can consider the expected present value if this is a continuous stream. So if $1 is not paid at the beginning of the year, but paid uniformly throughout. So if I have continuous annuities, the annuity of 1 is paid uniformly throughout. In that case, we have the following formulas. We have ax bar, which is the integral from 0 to infinity, nu to the t px dt. And we have the formula for a temporary annuity, so a bar x n will be the integral from 0 to n of nu to the t. Then we'll have a px t dt. In both these formulas we can write with the force of interest as well. So we know that nu is e to the negative delta. So this formula over here becomes the integral from 0 to infinity, e to the negative delta t, tpx dt. And so we can see, of course, that this is just a Laplace transform with the variable delta as my Laplace variable of the survival function as a function of t. Likewise, we can write this formula for the temporary annuity as the integral from 0 up to n, e to the negative delta t, tpx dt. Now we can consider other variants of these annuities. We can consider, for example, a deferred annuity. And deferred annuities are oftentimes used in retirement products where you make a series of payments during the deferral period and then get some annuity benefit later. So what will happen in this situation is you have your timeline. Here's time 0, and there will be a deferral period, 1, 2, up to n minus 1. And then after this deferral period, the annuity will turn on. So at time n, you'll get a payment of 1. At time n plus 1, you'll get a payment of 1. And those payments will go on forever. So the notation for this is you will have n bracket a double dot x. And we can see now there's a relationship between the whole life annuity, and we'll consider this as our discrete version. We have a whole life annuity, a temporary annuity, and a deferred annuity. We can see over here that there's a number of different ways to write this. This is exn, the probability that you survive, that x survives n years discounted, and then a double dot x plus n. And we can also see that if we do a bar x minus this temporary annuity, so we also have a double dot x minus the temporary annuity due is equal to this deferred annuity due, n-a-x double dot. And therefore we can write a-x double dot as a double dot x n plus the deferred life annuity due. And so those are our deferred annuities. And so any one of these representations can be used as a recursion to find one or the other. Finally, what we can do is we can consider one other special class of annuities. But before we do that, we want to make one more sort of note on the recursions. So let's look at this ax double dot and see if we can form a recursion using shifted annuities. This, by definition, is the sum. K goes from 0 to infinity, nu to the k, k px. Let's look at the first term over here. The first term over here is exactly equal to 1, and then we have the sum, k goes from 1 to infinity, of nu to the k, k px. So we can do the following. We can shift the index of summation down by 1 unit. So let's do that. We can write this over here as 1 plus the sum. K goes from 0 to infinity. If I shift this down by 1 unit, I have to add 1 over here to k. So I have nu to the k plus 1, and then k plus 1 px. And then we do our standard trick. We write k. We can take this k plus 1 p of x and write this as px. And then that means x survives 1 years, and then x's age is advanced by 1, so you're x plus 1, and then you survive an extra k years. We write this product, so I have a factor of a px, and I have an extra factor of nu. So what we'll do with this sum is we'll write this as 1 plus factor out of nu, factor out of px, and then we have the sum, k goes from 0 to infinity, of nu to the k, and then we'll have a k px plus 1, and this is exactly as a whole life annuity to someone age x plus 1. So what this is this is exactly equal to 1 plus nu px a, that will be an a double dot x plus 1. And so that gives us the following recursion, that ax double dot is equal to 1 plus nu px ax plus 1 double dot. And we can continuously turn this recursion over and over and over again and get a formula for a double dot x in terms of an annuity, a whole life annuity due at any future age. Thank you very much.